Good afternoon, everyone. I am Rishabh Kumar, and I will be presenting my research, the fire performance of hybrid fiber reinforced self-consolidating concrete with glass Pozzolan. The research was carried out at the University of Texas at Arlington under the supervision of Dr. Noria Stani and Dr. EOCS Penebero. So I will begin my presentation with this outline. So I will give a brief introduction about the topics, the materials that I have used in my research, and then I'll move on to the problem statement and objectives of this research. And entering the experimentation section, I will discuss the SEC mix design, the tests that I have performed on the specimens, the results, and finally end with the conclusions. So to begin with, we all know that the self-consolidating concrete has gained popularity because of its ability to flow under its own weight, and it's preferred for construction of complex structures and like it can easily fill congested areas and also provides various other freedom parameters during construction. Uh, Hybridization is a technique where concrete is reinforced using two different fiber types, basically the macrofibers and microfibers. So macrofibers are known to provide mechanical strength and toughness to the concrete matrix, while the microfibers help in reduction of crack propagations and also known to avoid fire spalling of the concrete. Typical examples of macrofibers are steel carbon and grass fibers, whereas for microfibers, we have polypropylene, polyvinyl alcohol, and polyethylene. Also, that we know that a lot of construction happens across the world. So the excessive use of cement is causing ecological concerns. So basically, it was reported that 5% of total CO2 release of worldwide is due to the production of cement. And in the United States, 2% of the CO2 release is again due to the production of cement. So we believe that there is a need to reduce use of cement consumption to certain extent, and hence we need to study some pozzolans as cement replacement materials. One such highly preferred material is the fly ash. However, recent research by Robel and McCormick show that uh, fly ash is not uh, abundantly available recently, and there are shortage for that, and hence there is a need to study other pozzolans. And one such material we considered is the glass pozzolan. USA is believed to approximately landfill 8.4 million tons of glass every year. By using this glass as the cement replacement material, at the same time we can target two environmental problems. That is, we can reduce the number of landfills in the America, and at the same time by reducing cement consumption, we can reduce the CO2 release of CO2. Uh, as my study involves exposure to fire, so the major the bigger concerns when it comes to fire is the concrete under fire undergoes mechanical and chemical changes. The major concern is the spalling phenomena. That's a mechanical that falls under mechanical criteria. So concrete, when heated, its relative humidity it tends to increase with the increasing temperature, and because of this, higher water content is results within the concrete matrix, and at higher temperatures, this water is converted to steam, and that steam increases the pore water pressure, which results in the spalling of the concrete. And I have few images that shows that how the structural integrity of the structure is damaged. So considering all these parameters, my problem statements are of concepts such as fiber reinforcement, cement replacement, and strength evaluation under fire for vibrated concrete has been studied extensively. However, these concepts for self-consolidating concrete have not been adequately explored. At the same time, hybridization is believed to have a good approach to enhance concrete performance, but how efficient does it is it under the action of fire is still under research. So that is something we wanted to test for SEC again. Like I said, that the increasing cement consumption has raised ecological concerns, so there is a need to study other pozzolans simultaneously. And again, the preferred Pozzolan here is the glass Pozzolan. And again, like I said, SEC, with SEC, there are very limited research that has substituted concrete for SEC and using glass Pozzolan. So we wanted to study the combination as well. So the objectives of this research were to review the existing literature on the types of fiber reinforced concretes, the fiber dosages, and cement replacement rates using other Pozzolans. We formulate different mixed designs with the appropriate amount of steel fibers, polypropylene fibers, and the glass Pozzolan again. Different trials were conducted to obtain appropriate mixed design as per the standard design specifications. Once we had that, we were to study the behavior of SEC with the materials like the hybrid fibers and the glass Pozzolan. We assess the strength parameters for these mixes before and after fire exposure. And finally, we have made comments on how hybrid fiber reinforced concrete helps against fire. Moving on to the experimentation section. So the SEC design mix was carried out as per ACI 237 R07 guidelines. So the slump flow of the SEC mix was, the workability of the SEC mix was set to 22 inches, and trials were carried out with all the materials to find the right mix design. And once we had obtained that, 4 different mix designs were 4 mixes were designed. That is the RSEC, the regular SEC, the GSEC, SEC with glass Pozzolan, the FSEC, SEC with hybrid fibers, and the FGSEC, that is the SEC with glass Pozzolan and hybrid fibers. On the right of the slide, you see the composition of different materials used to formulate these mixes. The highlights are that the cement replacement rate used for the glass used for the SEC was 20%. So 20% of cement was replaced with glass Pozzolan, and the dosage rate for steel fibers were 3.5 lbs per yard cube, and the dosage rate for polypropylene fibers were 1.5 lb per yard cube. These dosage rates were kept minimal so as to obtain the right workability of the SEC design mix. In total, 12 beams and 24 cylinders were cast, and the length of the beams were like 3 feet and 8 inches in depth and height, in depth and width, and the sizes of the cylinders were 4-inch dia and 8-inch depth again. Since we were to fire expose these specimens, we used thermocouples to study the surface temperature of the beams and cylinders. The tests performed on these specimens were starting with the slump flow test, that's the ASTM C1611, and then the fire exposure of specimens as per ASTM E119, 3-point bending flexural test as per ASTM C78, compression strength as per ASTM C39, and split tensile strength as per ASTM C496. Moving ahead with the results. With the first test, slump test, it was observed that the maximum slump was obtained for the GSEC variant, and that was even higher than the regular SEC. So basically adding glass Pozzolan to the SEC gave us a higher workability, and this has been previously observed by Ghaffuri et al. As well. However, introduction of fibers, especially the microfibers, that's the polypropylene, significantly reduced the workability of these mixes. And we can see that for FSCC, the maximum workability obtained was the 20 inches itself. So, like I said, the fire test was carried out as per ASTM E119 standard, and the fire exposure time was 30 minutes. And the maximum temperature the specimens were exposed to were 1550 degrees Fahrenheit. So these curves basically highlight the different surface temperatures. To begin with, I have the top surface temperature and the core temperature of the beams. So it was observed that the mixes with glass Pozzolan tend to have higher temperature gains when compared to the all other mixes, and the mixes with the hybrid fibers generally had very low temperatures. Moving on with the here I show you the bottom surface temperature for beams, and the other graph is for the cylinders. It can be seen that again GSEC again reports slightly higher temperatures, and you can see here that there is an abnormality observed in the the mixes that contain hybrid fibers. So this is basically because of the melting of polypropylene fibers. So research says that approximately at a temperature of 320 Fahrenheit, polypropylene melts inside the concrete matrix, and as it melts, it tends to create voids within the matrix, which these voids help in release of the pore pressure that is caused during the heating of the concrete. And due to this, these fibers, polypropylene fibers, microfibers, help us in avoiding any kind of spoiling. So similar results were observed that no spoiling was observed for the specimens, except for few damages to the edges of the beams. And the conclusion of the fire test was that the glass pozzolan basically acted as a thermal conductor. And previous researches show that it tends to act as a thermal insulator. However, exact opposite was observed in this research. Here I have a video showing the showing you the when the mixes are heated, we did observe the steam vapors and the condensed water. So these highlights what's happening within the matrix. That's what I explained with the polypropylene fibers. However, since SEC tends to have higher water content, so these vapors were observed for all the mixes. However, they were higher for mixes with hybrid fibers. My second video here represents the cracking. So basically, this video was added to show you the surface cracking that actually occurred due to the fire exposure of the specimens. Moving on to the results of these tests were, so beginning with the compressive strength, the maximum compressive strength observed at both the room temperature and the after fire exposure, that's the elevated temperature, were highest for RSEC and lowest for the glass pozzolan variant, that is the GSEC. GSEC generally tends to show strength gains over a period of like 90 days. This was reported by Zidol et al. At 2020. This is because of the slow pozzolanic chemical reaction that occurs in the glass pozzolan, and any kind of strength before 90 days is generally shows negative effects. The compressive strength in the mixes with hybrid fibers were between the two, between the RSEC and the GSEC, and it was observed that with the addition of hybrid fibers, the compressive strength decreased. However, no benefits of adding hybrid fibers was observed for compression strength. On the left, you see the failure types for these cylinders. So the type that we observed were type 2 and type 3 as per ASTM C39 code. And even after fire exposure, no changes in failure patterns were observed. They were pretty similar. Moving on to the splitting tensile strength, at room temperature, the similar pattern was observed where RSEC reported higher splitting tensile strength, and GSEC being the lowest, and the ones with the hybrid fibers being the intermediate. However, after fire exposure, as you can see in the graph, the maximum was reported for the mixes containing the hybrid fibers, and the highest being the FG-SEC variant. The reductions for FG-SEC and FSEC were 24 and 21%, whereas for regular concrete and for regular SEC and glass pozzolan variant, they were 33 and 25%. The pics at the bottom show you the typical failure patterns for splitting tensile strength. Moving on to the flexural strength, once again at the room temperature, the RSEC basically had the highest strength of 12.4 kips. And the second best strength observed was for GSEC and FSEC. They were both equal to 11.80 kips. And the combination of hybrid fibers and glass pozzolan had a negative effect on flexural strength. And the strength we observed were like only 9.4 kips. However, the similar mix after fire exposure gave us thrice the strength of when compared to the regular SEC. So the residual strength for FG-SEC was almost 9.918 lbs, And whereas for the RSEC, the residual strength was only in terms of 300 lbs, and a reduction of almost 98% was observed for the regular concrete without the hybrid fibers. So basically, after fire exposure, hybrid fibers benefited the splitting tensile strength and the flexural strength to a greater extent. So I'm trying to explain you the failure patterns before fire exposure and after fire exposure. So the image here basically shows the brittle failure that occurred for all the mixes before fire exposure, and the beam cracked at the midsection. However, these three images present a beam after fire exposure, where the failure occurred across the cracks that were developed during the fire exposure. The one, I mean, the video I was trying to show you. So basically, this is the left, the bottom, and the right face of a single beam, where you can see the crack propagation happens throughout the three faces, and that's how the failure occurred. There was no sudden failures, and the beams behaved ductile in nature. Here I have just the graphs for load versus displacement curves at room and elevated temperature. Once again, these highlight the ductile behavior of mixes with hybrid fibers after fire exposure, where we can see that displacement is relatively very much higher when compared to the mixes without hybrid fibers. However, at room temperature, like I explained, the failure was brittle and for all the beams, and this ductile behavior only appeared after the fire exposure. Similarly, I have tensile strains at room temperature, where this again highlights the brittle nature of the four different design mixes. So to conclude with the conclusions of this research were the workability of SEC tends to increase with the glass pozzolan, and generally higher with the higher replacement rates. However, hybrid fibers, especially the microfibers, reduce the workability very significantly. Glass pozzolan at the core of the beam acted as a thermal conductor and resulted in very high temperatures. And the temperature for the mixes containing hybrid fibers were minimal. It did not show any higher temperature gains. No benefits of adding hybrid fibers were observed for compressive strength, both at room and elevated temperature, and reductions were observed due to the presence of hybrid fibers for compressive strength. Glass pozzolan produced lower compressive and split tensile strengths, both at room and elevated temperatures. However, with the addition of hybrid fibers after fire exposure, higher splitting tensile strength is observed for both HF and GB, that's the hybrid fibers and glass pozzolan. In terms of flexural strength, again, initially the highest was for the RSEC, but with the introduction of hybrid fibers, the maximum was observed for hybrid fiber and glass pozzolan, and that was almost thrice the regular SEC, the residual strength. All the beams at room temperature acted as a brittle failure, and however, the mixes RSEC, the mixes GSEC, HS, FSEC, and FGSEC were, however, ductile at elevated temperature, where RSEC was still a brittle failure. So basically, the fibers help in converting the brittle failure to the ductile failure at higher temperatures. So thank you for listening.